Okay, we're continuing on here, chapter 11. We were talking about obviously electron configuration, orbital diagram. Again, a reminder that if you know S's could hold 2 electrons maximum, P subshell could hold 6, D subshell could hold 10, and F subshell could hold 14, along with again being able to recreate sort of the proper order of the electrons, which you could do by again, just remembering where each of those sort of orbitals begin in terms of energy levels. Again, S's start on the first energy level, P start on the second, D start on the third, and F start on the fourth energy level is where they begin. And that allows you basically just to do the, as we talked about, kind of go 1s down to the right a little, 2p, 3D, and 4F. And really just kind of go diagonal like that. All you have to do is just fill in the numbers underneath with the same letters and just go up to like 7. And you'll have the proper order by, again, just kind of filling it in. With the right letters would be good. Oh, there we go. 5S, 6S, 7S, 2P, 3P, 4P, 5P, 6P, 7P, 3D, 4D, 5D, 6D, and 5F. And in a matter of, just very quickly, you have basically just recreated that sort of chart that you could use to get the proper electron configuration. Remember, we also show orbital diagrams, which are boxes or lines that represent each of the orbitals. And again, when we fill orbitals with the orbital diagram, there's a few rules that we follow. Pauli's exclusion rule tells us the first one's going to go up. The second electron within the orbital needs to go down in the paired position, or not really, when this becomes paired spin. Again, that follows suit as well. Hund's rule tells us the most stable in sort of a subshell is to maximize parallel spin. So when we get to like P or subshells, D subshells, and F subshells, we always fill them in the upwards direction first, 1 electron per orbital. Then we come back and we fill in the rest, going in the opposite way. We also talked about sort of shorthand, 1s2, 2s2, 2p6, 3s1. Once again, if you look at sort of the electron configuration here, you count up the top numbers, that is 10. If you look on the periodic table, 10 is neon, which is a noble gas, so you can kind of shorthand the configuration by putting neon in brackets there. And that represents basically neon's electron configuration. And then you could just continue on with the configuration like normal there, and you get 3s1. It should always be a noble gas that goes in the brackets, and it should always be the noble gas that comes right before, thank you, whatever element you are writing the electron configuration for. We also got into transition metals. Remember, the first row transition metals actually occur right about here. So as we kind of come through here, it is the 4s that comes first, followed by the 3d. So remember, in terms of filling order, the 4s orbital is lower in energy than the 3d. They are very close to one another, but they are lower in energy, so they actually do get the electrons first before we start filling the 3d orbitals. So that is again sort of the not all threes together. You kind of go back to 4, and then up to back down to 3 again. Um, there are a couple of exceptions that you're responsible for, which is chromium and copper within the transition metal region. And again, the exception is that they have one less electron in the s orbital and one more electron there in the d, something for chromium. Same deal for copper, has pretty much the identical sort of deal, one less in the s and one more up in the d. Once again, there is more exceptions, as we'll see here in a second, which we talked about last time. If you go to copper and chromium on the periodic table, pretty much go down and in. There's a lot of those similar exceptions, but for us in this class, and probably most chemistry classes you take, those are the two typically they make you remember is chromium and copper. Any questions on any of that there? All right. So speaking of those two, again, you can see those are the exceptions of the normal filling order. Again, just been found experimentally to be more stable. As I mentioned before, and again, you won't be responsible for the other ones here, but just so you know, again, you can see those are our two, and that's what you would normally get if you just follow our normal filling order. Experimentally, have been found to be more stable in this arrangement, and you can see something like PD, for example, here has no electrons. They've all been kind of moved up to the D. So most of these elements here are below chromium and copper on the periodic table and in. And so there's a lot of exceptions in that area. Now, the lanthanide and actinide series, which are the two rows that are on the bottom of the periodic table, that's really where F orbitals sort of begin, and you get to the F orbitals when you get down there. They have incompletely filled F subshells, and they do give rise to cations that also have incompletely filled 4F subshells. So just to show you some more of those there, there we go, maybe. So you can see as you kind of go underneath copper and chromium and then kind of come in, there's a lot of those sort of exceptions that are occurring. Again, you see some there and RPD and so forth. So there's a lot of those sort of exceptions. Once again, you won't be responsible for all of them. Just those two, chromium and copper, are the two that you'll be responsible for. Now, when you look at the periodic table, you could actually count off electron configuration from the periodic table, uh, understanding where things are. So the first two groups on the periodic table are what are sometimes referred to as the S block, and that's because, right, S hold two electrons. That is 1 and 2, basically. Groups 3 through 8 is the P block. P subshell could hold 6. 1, 2, 3, 4, 5, and 6. The transition metals are the D block on the periodic table. D could hold 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And the F subblock, which is our 2 on the bottom there, could hold 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. The period numbers are the end values. So period 1 is n is equal to 1, period 2, n equals 2, and so forth. And you can, again, like I said, sort of count off electron configuration by doing so. So for example, let's say we had potassium, which is 19, which is right about there. Potassium. And we wanted to sort of count off its electron configuration. So what we would do is we would start up on top, and as we would come across to here, that would give us a 1s2. We now would have a 2s2. All the way across there would give me a 2p6. These guys right here would give me a 3s2. All the way across here, 3p6 and 4s, as I run out of room there, 4s1 there at the end. So you can literally sort of count it off. Now, again, if you were doing maybe somebody over at like sulfur, for example, it's some of those here. Those that were doing sulfur, which is right there. We want to go to sulfur. Once again, always starting at the top, all the way across here would get us 1s2. coming here, 2s2. This is 2p all the way to the end, would be 2p6, 3s2. And now this is 3p, 1, 2, 3, and 4. 3p4 in that case. So again, you could just count it off where they end. You do have to be careful because there are some places that perhaps if you not really careful what you're doing, you might run into some trouble. So let's just say we wanted to do, let's do iron hanging out right about there. Once again, coming this way, 1s2, 2s2, 2p6, 3s2, 3p6. Remember here again, 4s is next. Now, people tend to mess this up because you're on the fourth period, but we know that d orbitals, which are right there, start on n equals 3. So once again, over here is 3d, not 4d, and it is 1 behind the period number, and that would be 3d, 1, 2, 3, 4, 5, and 6, and that would get the, okay, so you have to be careful. The d orbitals are 1 behind the period number. Down here would be 4d, as you can see, 1 behind, 5d, 1 behind. Also, if you happen to get yourself down in this area where we're into the F's, you also have to be careful because remember that these two rows on the bottom technically go right there, right? And that is actually 4F, which is actually 2 behind where it should go. So it's 2 behind the period number, and 5F below it is also 2 behind the period number. So it gets a little crazy if you're counting off of the periodic table and that kind of transition metal region. Definitely if you get into the F's, you just got to be careful in terms of the numbers. But otherwise, you could do it. Careful, I suppose. But for all the chart thing, you should be in good shape. And the electrical configuration you want to do. Yeah. Or you other shorthand the first S block with helium. You can for technically for anything that comes after helium, I guess, if that's what you're asking. Yeah. So if you have like lithium, technically you could do helium and then 2s1. Yeah. You can if you again there. I would probably recommend the other chart to be honest with you because that'll probably give you always the right answer. Again, if you understand what you're doing, especially when you get into this transition metal region of the numbering, that you don't. I've seen people come through here and just start going because to get the 4. Because remember, you're not going to have the pretty little numbers like that, right? It's going to look more like this, right? So when people do it, they go, oh, 4. Oh, I know this is D and it's on 4. So they very commonly go like 4D there instead of 3D, which is what it should be. So, you absolutely need it. You're just careful in those spots. Other questions? All right. Let's talk a little bit about, whoa, there it is, electron configuration for ions. So obviously ions, as we've talked about previously, are things with charges, and there are cations and anions. And as we talked about before, cations are positively charged. That is a result of losing electrons, and ions are negatively charged. Uh, so because they either lose or gain electrons, we do have to adjust the electron configuration when we are writing it for something that is an ion. So for example, if I had calcium with no charge, that is 20. Which means if we follow our chart and write our electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, and a 4s2 happening there. Calcium is group number 2, which means it will form a +2 charge. So when calcium forms a +2 charge, it will actually have 2 less electrons and actually have 18 electrons. And because of that, its configuration would be 1s2, 2s2, 2p6, 3s2, 3p6. Now, if we count up all of these, which obviously equals 18, and we look at the periodic table, number 18 is our friend argon. Yeah. So calcium there with a charge has reached argon's configuration. If we take a look at sulfur, which we did a second ago, and sulfur there being 16, its configuration 1s2, 2s2, 2p6, 3s2, 3p4. Sulfur, which is group number 6 on the periodic table, will form a -2 charge and will actually gain 2 electrons and will end up at 18 electrons. And again, that's what the charge means. 2 is how many electrons, and minus means it gained. It will end up with a configuration of 1s2, 2s2, 2p6, 3s2, 3p6. And what we see here is that again is 18, which is argon's configuration. That is, as we will talk about in the bonding chapter coming up, the basis of all bonding is for everybody to become very similar to the electron configuration for the noble gases because they are very, very stable. So all three of those things, calcium with a +2 charge, sulfur with a -2 charge, and argon, they all have the same electron configuration. They are what are known as being isoelectronic with each other. Isoelectronic means that they have the same electron configuration. Now, as I think we've talked about previously, we know that calcium and sulfur do not become argon, and that is because we do not change the number of protons, right? So because the protons are not changed here, calcium and sulfur are still calcium and sulfur. They become like argon in the sense of their electron configuration is the same as argon. That makes them stable. The purpose of bonding, like I said, is for everybody to basically reach that noble gas configuration. The way that metals and nonmetals are able to do that when they come together, make, for example, an ionic compound, is metals will lose enough electrons to back up on the periodic table to the noble gas that comes before them. So if you take a peek on the periodic table, you will find calcium here, and if you back it up to group 8, argon is there. So metals will lose those electrons. Representative metals will lose enough electrons to back up to that noble gas configuration. And if you look at the periodic table, nonmetals like sulfur will gain enough electrons to move forward on the periodic table to the noble gas that comes after them. And that is actually the basis of an ionic bond, is that is what makes the ionic bond stable, is both of those things, when the metal and the nonmetal come together, that gas configuration, which makes everybody really stable and makes for a stable sort of association and bond to happen. Now, transition metals are a little bit different in terms of what happens when they lose electrons. And since they are transition metals, they will always lose electrons. They will never gain electrons, so they will only become positively charged. And let's just take a look at our friend iron, for example, that we just did, which was 26 there. So once again, if we write the electron configuration for iron, we're going to have our 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6 are the shorthand there, argon, 4s2, 3d6. So we're really going to focus in on what happens here when atoms lose or gain electrons. It really involves usually only what are known as the valence electrons, which are the highest energy electrons, those kind of guys at the end. So when iron, for example, gets filled with electrons, and really any transition metal or any element that this occurs at, the electrons will again fill to the 4s first based on our order. It will then start to fill the 3D because, again, it's higher in energy at this point, and it's going to put its 6 electrons in properly, right, all going in the upwards direction and one coming back down in the downwards direction there. And that's sort of what neutral iron looks like as it's getting filled with electrons. Now, one of the kind of interesting things that happens with these orbitals are once you actually start to populate the d orbitals, there's actually a switch in energy that occurs. So as you start filling in those d orbitals, these two energy, the energy of these two sort of orbitals and subshells, they actually switch. And what ends up happening is after you start filling those d orbitals, the 4s orbital actually ends up being higher in energy than the 3d orbital. So this is kind of switch in energy that occurs after you start populating really your d orbital. Now, this is really important for something like iron or other transition metals because that affects what happens when they start to lose electrons. And as I mentioned a second ago, typically when they lose electrons, they will lose those highest energy electrons first. And in this case, and in the case of pretty much all transition metals, at this point, the highest energy electrons are actually the S's, and they will actually lose the S electrons first. Now, another very interesting sort of aspect of transition metals when they kind of lose electrons is, unlike what are known as representative metals, which are group 1, group 2, and group 3, the transition metals actually have available to them a lot of electrons to lose. They could also lose some d electrons as well. So if they needed to, they could lose their s electrons, and if they happen to need to lose a few more, they could dip into the d after that. But the first ones that always get lost are going to be those s electrons. So what happens if iron makes a +2 charge? Get rid of my little circles there. So if we had iron with a +2 charge here, that means instead of its 26 electrons, it has lost 2 electrons and now has 24 electrons. And its configuration will be argon. And the 2 electrons it's going to lose first are the s electrons because they are higher in energy. So it would be argon 3d6. And again, sometimes people screw up the transition metals because they're used to kind of taking the electrons out of the very last thing written in the electron configuration. But here it actually is those 4s. Now, if iron made the +3, which it can because it can make a variable charge, if iron had a +3 charge, it would go from 26 to 23 electrons, which means it would be argon. It would again lose these 2 electrons, but now it's out of s electrons to lose. So the next sort of highest would be losing an electron out of our d orbital, and it will end up at 3d5. Yes, sir. So two kind of stable or most common oxidation states of iron are actually 2 and 3 is pretty much what it does. And it's for kind of that reason with 2 because it kind of eliminates those high s electrons. And then the 3 sort of maximizes definitely at that point, right? So parallel spin, but it has some other factors involved in that. But there's one. Yeah. So the other thing that you also will notice is transition metals do not back up to noble gas configuration, right? So that's because they have a lot of electrons to do that. Something like, for example, iron would have to lay up a lot of electrons to get all the way back to the normal gas configuration. It's not going to happen. Obviously, it has at least 8 electrons plus two more. It has to give up like 10 electrons, have a plus 10 charge. It just doesn't really happen in that case because it doesn't need to do that. Yeah. Yeah, so the good thing about that is it will never happen because these are transition metals. They only will pretty much lose electrons, so not gaining electrons. So remember that only really non-metals, which are the upper right of the periodic table, are the ones that will gain electrons. So you'll never really have that situation. In theory, if it was a negative charge, it would go forward. But no, that you will never come across anything like that. So metals will always lose electrons, become positively charged, and non-metals will gain electrons, become negative charge. Yeah. Yeah. So in the case of that, there are a couple up in the front of it that could potentially get there. And like I said, as you go through the transition metals, they have common oxidation states or charges that they typically make. And for the most part, in that transition metal region, twos and threes are very common, and occasionally fours. The if you go like almost dead center in the transition metal region where you have Mn, that guy can have in certain situations like 6 or 7 different oxidation states. So it kind of like peaks in the middle. So in terms of like their charges, oxidation states, it kind of increases as you kind of get to the middle. Then it kind of comes back down. Where most things there, like I said, I would say plus two, plus threes are very common, and then plus fours is kind of what you get. So if you kind of think about the location of most of those, that's going to either overshoot, not really get back to the noble gas configuration. The good thing about it is we don't really deal too much with those guys in terms of bonding and stuff like that, so we don't have to worry about them. Yeah, so this is only for what we're talking about is all the metal. Look at the transition metal region, which is this here. We're only really talking about this happening really for all these guys here, all these transition metals, basically. And all those guys will always kind of lose those S's for because they all have that situation happening. The S and the D's are super close in energy, and the filling order is first, and then that third. That's also why this we're talking about here online in some places that people will write the like configuration. It looks like they're writing it all like for example, you may see some but write like iron and go like 3s2 6 3d6 and 4s2. And that's the electron configuration based on energy after all the electrons have been put in there. And nobody really writes it like that in classes that you take. Like I think I might have said the other day, I think I only took one class ever where you had to write it like that. Everybody writes it in filling order where the S's get filled first and then the D's. And but technically speaking, it is correct after it's filled that that switch happens and it does sort of bring it back into order and stuff like that. So it does affect how the electrons are taken out. Really, what we're talking about here is strictly for your transition metals. That's going to happen. You don't have to worry about it here because once they lose those electrons, they only have enough valence electrons to back that here and stay up there. And it will always be the last electron sort of written in your electron configuration for anything that's not a transition metal. So if you write electron configuration for everybody here or really aluminum, you're going to be picking off those ones at the end of the electron configuration that you wrote is just the transition metals because they have that kind of switch in those orbitals energy that we take the S's first and then come back to the D's. Other questions? All right. And for the most cases, because all these representative elements do back up always to the noble gases, is typically always those last electrons in the configuration, which are the valence electrons, and you typically take out all those kind of last electrons to get kind of back them up there. All right, so why don't you try a couple here? Why don't you do, let's do right the configuration for sodium. Let's go with nitrogen there. And let's do Mn4 plus. Obviously, these 11. Nitrogen is 7. And Mn. Okay, so let's take a look. So I'm going to look at sodium, which is 11. And if we did sodium with no charge, it would be 1s2, 2s2, 2p6, and 3s1. Now, sodium with a +1 charge means that it does have 10 electrons. And it is going to be, as you can see, this very last one that's written. This is really sodium's what's known as valence electron. And again, that is the highest energy electron. It's the one's really involved in bonding. And that is actually the one it's going to lose when it loses that electron. That's going to leave us, obviously, our 1s2, 2s2, 2p6, which is obviously neon's configuration. Again, because sodium is a representative element, it will back up to a noble gas and end up at the noble gas that comes right before, which in this case is neon. Any questions on that one there? Take a look at the next one, which is nitrogen. Nitrogen, which is 7. Once again, neutral nitrogen, 1s2, 2s2, 2p4, 3. There, the count maybe. So that's 3, 5, 7. When it gains electrons, it's going to go from 7 and gain 3 because that's the -3 charge. It also will end up with 10 electrons when it has its charge. That's going to yield us our same electron configuration, 1s2, 2s2, 2p6. Once again, it is going to lose these electrons here, which is also its valence electrons, and we'll end up in neon's configuration. Now, if we look at sort of the orbital diagram for nitrogen, it's got this, and then it's got 1, 2, and 3, right, for our GP. Now, nitrogen actually has 5 valence electrons because we look at its configuration, it ends with 2s2, right? 3p3, I'm sorry, 2p, there we go, 2p3. And that is 5 electrons, both on the second energy level, which is the highest. In this case, nitrogen's only going to give away, are going to accept, in this case, 3 of its electrons. So it's not going to really give them away. I guess I shouldn't really box them out, huh? No, it's not right there. It actually has room for those electrons coming in, and where it has room is right there. Those are going to be the 3 electrons that are going to come in this case, as it gains those electrons. Any questions? So nitrogen is able to achieve noble gas configuration because in this case, it has room to accept those electrons that are coming in. Now, when we look at Mn with a 4 plus, normal is 25. So that's going to be argon 4s2 3d5. And this would be, again, Mn with no charge. When it loses 4 electrons, it's going to have a switch in energy that's going to occur. So if we just kind of look at the last part of it there, we already have switched the energy. So it's got to lose 4 electrons and it's going to take it down to 21 electrons in its charge state. Again, because it's a transition metal, it's going to lose the 2 of those s electrons first. Now it has to delve into the d and take out a couple of electrons there. And that's going to leave us now an argon 3d3 in terms of its electron configuration at this point. Any questions on that? Yeah. All right, so obviously you need to be able to write electron configuration for neutral things with charges. Yeah, yeah. How does it say again? It's gaining, yes, it is. Yeah, it's gaining. So like before I put the blue arrows there, it's was filled, obviously that 2s was already filled with electrons. When we look at the p subshell, it has just the 3 red arrows or electrons to begin with. So that 2p subshell had room for 3 electrons that it's going to accept, and that's where it's coming in. And by doing so, what it does for nitrogen is it actually moves it forward on the periodic table, right? Because it's now gained electrons, and it moves it forward towards neon configuration and ends up at neon's configuration. And that's different than sodium that had to kind of lose an electron to kind of back up to reach the noble gas configuration. Other questions? Okay. All right, so speaking of valence electrons are really important electron. There's really kind of two types of electrons now. There are core electrons and valence electrons. So if we do look at nitrogen here, again, just neutral nitrogen, 1s2, 2s2, 2p3. Nitrogen here has 5 valence electrons. These are the electrons that are the highest in energy. Now, also, these electrons that are not highest in energy or not valence electrons, they are sometimes referred to as core electrons. And core electrons are the electrons that are lower in energy. They're closer to the nucleus, and they're held tighter because of that, and they're not involved in bonding. So the significance of valence electrons are they are the electrons that are involved in bonding. So if you think about it, they are the highest energy electrons. They're on the kind of the outside of the atom. So they are the ones that come in contact with electrons in other atoms that are also farthest away from the nucleus. You could do that for anybody. If you looked at lithium, little 1s2, 2s1 action. This is the highest energy level, has 1 valence electron. If you look at sulfur that we looked at previously, 1s2, 2s2, 2p6, 3s2, 3p4. Sulfur has up to the 3rd energy level and all of these electrons here, and that is 6 valence electrons in the case of sulfur. Now, you could definitely write electron configuration to figure out the number of valence electrons, but nobody wants to do that. So the easy way of doing it is the number of valence electrons equals the group number on the periodic table. So nitrogen is group number 5 on the periodic table. It has 5 valence electrons. Sulfur is group number 6 on the periodic table. It has 6 valence electrons. Lithium, which is down here, has group number 1 on the periodic table. It has 1 valence electron. So super quick way, and the way I would recommend figuring out valence electrons is it equals the group number. It's a super quick way of obviously getting that. Very helpful when you get to the bonding chapter. You don't have to write out the electron configuration to figure out how many valence electrons. You can just look at the periodic table to figure it out. Any questions on that there? Now, you may be asking, what about our transition metals? Well, the good news on transition metals is, I'm sorry, yeah. Yeah, no, noble gases will have 8. Yeah, so it goes all the way through 1 through 8. And we're talking about our metal and then through 8 in terms of the 8. It would have 8 electrons. 8 valence electrons is a really important number. It is really super stable, which is why they don't really looking to do much because they're kind of filled. And that's also why, as I mentioned before, that's the basis of bonding and why everybody else wants to get there in terms of their electron configuration. They get to that mass number of 8, which is a big number of bonding, that allows them to achieve that noble gas configuration. Now, you may be asking about the transition metals. Uh, it also equals the group number. Let me just find that chart here. This might work. Do I have one? I think I do, maybe. We'll just borrow this here. So when we're talking about the transition number and I'm sorry, we're talking about the valence electrons and the transition metals. We actually use not the 8 numbering to figure out how many valence electrons it has. We use just the regular kind of 1 through 18 numbering. So if you go 1 through 18, that takes care of pretty much all the groups there. And when you get down to transition metal, this would be right 1, 2, and then basically 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And that's the numbering that we would use for valence electrons for transition metals. So if we take a look at what we had in terms of, say, iron that we wrote earlier, iron was argon 4s2 3d6. And these here, as we were talking about, these are the ones that they will lose for when they gain charges. That is iron's valence electrons. If you add that up, that is 8. And that is out there. If you take a look at something like chromium, that we also wrote the electron configuration previously for, argon 4s1 3d5, that is 5 and 1 is 6. Yeah, so also could use it for our transition metals as well if you just need to quickly figure it out. That's what I was saying before. Technically speaking, something like zinc has 12 valence electrons, and something like zinc, in order to get all the way back to a noble gas, it has to lay up like a plus 12 charge. And again, it's just not going to really happen energy wise. It won't do that. Zinc will actually lock in at just 2, basically. So it'll just lose those 2 s electrons. So if you want to quickly figure out you want to quickly figure out valence electrons for transition metals, you want to use kind of just the regular numbering 1 through 18 through that section, and that'll tell you basically what they are. Any questions on that there? Yeah, so like I said before, the good news is we don't really deal with transition metals and bonding, which is really probably where you will kind of apply this in the same thing. We deal with just the regular sort of representative guys, the A guys, and those are, what you would use. So representative guys also still roll really with the same, number as well. It's just down here we want to kind of switch back to 5 rather than 15, and valence electrons and stuff like that as you kind of go that one. All right, there. All right. So F has 7 valence electrons, group 7, also chlorine as well, and carbon there has 4. Now, metals and nonmetals, as you go down a group, especially with metals, they give electrons a lot easier. So if we look at group 1 there, cesium will lose their electrons a lot easier than lithium. And that is because their outer electrons are further away from the nucleus. And because of that, those valence electrons are not held as tightly for some reasons we're going to talk about here in just a second. And that allows them to be removed a lot easier. Now, the most active nonmetal you could have is up right on the periodic table. So up and towards fluorine, up and to the right is where you find the most reactive nonmetal. Most reactive metal is down and to the left on the periodic table. Reason for that is some of these periodic trends that we're going to talk about now. So let's talk about some of these periodic trends. The first one is effective nuclear charge. And effective nuclear charge is the positive attraction that, say, valence electrons experience. Now, remember that opposites attract each other. So the electrons, which are negatively charged, are attracted to the nucleus, which is positively charged. And in general, the attraction between something that is positive and something that is negative increases with the size of the charge. So something that's like +4 and -4 are going to be held a lot tighter than something like a +1, -1 charge. They're going to still be held together, but not as strong as a larger sort of charge. So when we look at it, just a simple example to demonstrate this: lithium, 1s2, 2s1. It has our one valence electron, as lithium is group number 1, which is this guy. It has our 2 core electrons, which are closer to the nucleus, which are those guys. So if I just draw a idea of what's happening here, the nucleus in lithium will have a +3 charge that has 3 protons in it. So it's got a +3 charge because of that. And obviously not drawn perfectly right, but just for this demonstration, on our first energy level, we got a couple of electrons hanging out. Those are our core electrons there, right? On the second energy level, flying around there, we have our valence electron, basically. So what happens is, because those 2 electrons, those core electrons, are sitting close to the nucleus, they're going to feel the full brunt of that +3 attraction. And that's going to kind of lock those guys in pretty tightly, because now they're getting like the full positive attraction, right? Like a giant magnet pulling them in. Now, what happens though when we think about our valence electron is this: because our valence electron is a little higher in energy, it actually experiences what is known as shielding. And what that means is it is actually shielded from the full brunt of that positive charge in the nucleus, and it is shielded by these lower energy electrons. So these lower energy electrons are sort of blocking the full effect of that +3 charge on that valence electron. So it's kind of like in the movies where you used to pick your seats, right? I think you roll in there, you get your nice seat right dead center, right? And nobody's in front of you. You got perfect view of the screen. And then right before the movie starts, somebody comes in with a giant hat, right? It kind of shields out half of the screen. You can no longer see really well. And that's sort of the same idea here. So what happens is, because that valence electron is experiencing shielding, it is not actually feeling that +3 charge. You can actually calculate it, and that is what Z effective is. You take the positive charge of the nucleus, or how many protons you got. You subtract from it how many electrons are shielding that other electron, which is 2. And now that outer electron here is only experiencing a +1 attraction to this, rather than the full brunt of that +3. That's going to mean it is still hanging on, obviously, because it still has an attraction, but it is not hanging on as strongly, right? So if you think about the magnet sort of thing, right? If you have an item that's going to be attracted to the magnet, but it's kind of far away, you could kind of pull it off pretty easily, right? Or move it out of its way. If you have something right onto the magnet, it's just going to get sucked into it, right? And be held a lot tighter. And that's sort of the idea here. So effective nuclear charge is positive charge that valence electrons feel as a result of shielding. That again is one of the reasons why valence electrons are involved in bonding, and why they're easily removed from the atom, rather than the core electrons, which you got to really try to rip them out, and it doesn't happen under normal conditions. And when you look at the periodic table, the effective increases as you go up to the right, and it decreases as you go down into the left. So you just think about what we talked about a little bit so far. As I go up and to the right, those are our nonmetals, right? And those are things that typically will attract electrons and hang on to their electrons. And to the left on the periodic table are metals, which will be very happy to sort of just get rid of electrons and use those electrons. Also, as you go to the right on the periodic table, a lot more protons, right? A lot more protons builds up the positive charge, right? So even the outer electrons, as you go to the right on the periodic table, are still feel a stronger as the nucleus has protons to begin with. Going to feel a bigger attraction to the nucleus on the left-hand side of the periodic table, where they have less protons, and the positive charge is not going to pull everybody in as close. Another really important ionization energy. And ionization energy is the energy required to remove an electron in the gas phase. Electrons, by the way, they actually do come off one at a time. So they don't all just at once. For example, if you took something like magnesium, the very first thing that would happen is magnesium would lose one electron and it would be given off. And the electron would be on the product side here, like it's being lost. In order to do that, that is what is sometimes referred to as the first ionization energy. So the first ionization energy is the energy to remove, for example, your first electron in magnesium. The next thing that would happen is this guy that has a +1 charge will drop off another electron. And that is known creatively as the second ionization energy, required to remove the second electron. Then maybe it wants to do another one here. So it got +2, becomes a +3. That would be the third ionization energy, right? Do you think it gets easier or harder to remove electrons after you already started removing one? Does it get easier or harder? It does get harder because what happens, electrons, right? The atom actually will shrink because you lost electron density, right? That's going to move whatever electrons are left closer to that positive charge of the nucleus and now going to be held tighter. Then you lose a little bit more electron density, going to get a little bit smaller, going to move those electrons closer to the nucleus. So it progressively gets harder and harder as you continue to remove electrons because those new electrons are now kind of moving closer to the nucleus, now getting closer to that magnet, going to be held a little bit tighter, going to be a little bit harder to remove. So the general trend as you go from first ionization energy to second to third to fourth or however many you have is it increases the ionization energy as you go from like first to second to third, etc. So it kind of increases as you go that way. Now, metals typically have very low ionization energies. Non-metals have relatively high ionization energies. Now, if we take the example that we just looked at there, which is magnesium, and we write its electron configuration, 1s2, 2s2, 2p6, 3s2, magnesium has how many valence electrons? It is 2. It is group number 2. It is these two here, right? These would be core electrons, right? This is valence electron territory, right? Yeah. Thing in the equation for configuration. It is for representative elements and the A groups, not the transition metals. But even in the transition metals, I put that way. I guess I'll put that. It is for everybody, but when they lose it for transition metals, it's not the last ones that are written. But even for transition metals, it is the last ones that are written. But if you're going to take away electrons, like we talked about, it's not the last ones that you take away first with transition metals. You see what I'm saying? So to answer your question, yeah, it is the last ones that are written. But remember, when you get to like transition metals, you have both the 4s, for example, and the 3d that are transition that are valence electrons. So yeah, it is still the last ones written. But if you're going to remove them, it's not going to come from the last ones, if that makes sense. Transition metals, it is both the S and the D are the valence electrons, but if you're going to remove them, like we talked about, you got to remove the S's first and then the D's. For the representative ones, it's always the last ones to get removed. Yeah. All right, so when we take a look at this, it has 2 valence electrons, and the rest are core electrons. So what happens is magnesium, because it's group 2, will only form a +2 charge. And the reason for that is we could take off the first electron because it's a valence electron. Going to cost some energy to do so. Not too bad, so that's going to happen. We could then remove the second electron, which is still a valence electron because it's still furthest away from the nucleus. It's going to cost you a little bit more energy than it did to remove the first one. So you're all good. But what happens after I remove the first two? I am now going to have to dip into these core electrons, which you're going to see a jump in energy that is so big, it's not going to happen. Yeah. And it's just not energy efficient for that to happen. I heard one out. You now are in core electrons, which, by the way, have also everybody's kind of shrinking down as you start removing those valence electrons. Going to find this stuff obviously much closer to the nucleus and get a lot tighter. So, not as big like certain things, for example, on the periodic table have fixed positive charges because energy-wise, you're getting into core electrons, and it's not feasible to try to remove those because it takes just so much energy to try to pop those guys off. So the first ionization energy, that is the general trend. As we go up to the right, it increases. As we go down and to the left, it decreases on the periodic table. Just to demonstrate what we were just talking about, this is the actual, for example, energy values to remove an electron. This is the first ionization energy for the first electron, second, third electron, fourth electron, and fifth electron. And let's just take magnesium, for example. To pop off that first electron is going to cost you about 735 kilojoules of energy. To take the second electron off, you can see it pretty much almost doubles, right, in the energy to remove that second electron, a lot harder to do so. But then it kind of jumps almost 6 times the amount if you wanted to try to rip off that core electron, and it's just not going to happen in terms of magnesium. You can even see for aluminum, which is group 3, aluminum typically will form a +3 charge because it has 3 valence electrons. First valence electron, 580. Then it gets a lot harder there as we remove the second one at 1800. To pop the third one, we're at 2700. And now you're going to get into that fourth one, which is the core electrons. You can see the giant jump in energy cost to try to pop that guy off. And again, not going to happen under normal conditions. So we won't see that occur. And again, that's why something like aluminum will lock into a fixed +3 charge. That energy cost. Any questions on that there? Another important trend is electron affinity. Electron affinity is the energy change that occurs when an atom gains an electron. So ionization energy is the energy to remove an electron. So we associate ionization energy with cation formation because they lose electrons, become positively charged. When somebody gains electrons, they become negatively charged. So we oftentimes associate electron affinity with it. And when somebody gains an electron, we see that the electron affinity increases as you go up and to the right, decreases as you go down to the left. Electron affinity should not be confused with another term that we'll talk a lot about in the next chapter, which is electronegativity. Electronegativity is the ability of an atom to bring electrons towards itself. Electronegativity also increases as you go up and to the right. By the way, fluorine is the most electronegative element you could have, and it decreases as you go down. So electron affinity is actually the energy change that occurs when somebody gains an electron. Electronegativity is the ability of that element to bring electrons towards itself. Not surprisingly, they kind of go in the same trend. So if you're good at bringing electrons towards yourself, you're probably pretty good at gaining electrons, right? So you're able to kind of bring the electrons near yourself, and you're able to gain them. So you have high electron affinity and high electronegativity as you go up and to the right. Now, all of these trends also correlate to the size that we see in terms of the atomic radius. By the way, when somebody gains an electron, they become larger in size. So the negative ion is bigger than the neutral because their electron density increases as they gain those electrons. So atomic radius actually decreases as you go to the right and increases as you go to the left and down on the periodic table. Um, and that's what we see here. We see that the size gets smaller as you go to the right. Again, we have a greater effective nuclear charge, going to have a greater positive charge of the nucleus. It's going to pull everybody in, just begin with, tighter because of that larger positive charge for those protons. And to the left and down, we just have a lot more protons and electrons. Our electrons really to fill, so they have to kind of spread themselves out. So how do all these trends sort of relate to each other, just to wrap up these sort of periodic trends here? If we look at all the periodic trends we talked about in the periodic table, we have the effective nuclear charge increases as you go up and to the right and decreases as you go down. We have our ionization energy, which is the energy to remove an electron, increase as you go up and to the right and decrease as you go down. We have our electron affinity, which is the energy change when you gain an electron, increase as you go up and to the right, decrease as you go down. We have our electronegativity, increasing as you go up and to the right on the periodic table, decreasing as you go down. And we have atomic size, decreasing, the only one decreasing up and to the right, and increasing as you go down. So when we think about all these things together, as you go up and to the right on the periodic table, you have things that are much smaller in size, which means even the outer electrons are closer to the nucleus. You also have a larger effective nuclear charge, so even those outer electrons are going to feel a much stronger attraction to that nucleus. And you have things that, because of that, will hang on to their electrons and actually bring electrons towards itself. And what that means is everybody up here likes to gain electrons. And what's up here on the upper right of the periodic table, those are our nonmetals, yeah? And that's why nonmetals, because of these periodic trends, typically will gain electrons. If you roll the other way, you have things that are much larger, which means their outer electrons are further away from the nucleus. They have a smaller effective nuclear charge, so those outer electrons are not even feeling as strong of a pull to the nucleus. They could care less about hanging on to their electrons. In fact, it doesn't take a lot of convincing for you to get them to give away their electrons. And all that means that as you go to the left on the periodic table, you find things that like and the left of the periodic table, those are no. And that is also what we'll talk about in the next chapter. When you take a metal and a non-metal and they get together, you have the perfect storm of metals like, take my electrons, I don't care. Non-metals like, cool, I'm looking to take some electrons. And that is why we get a ionic compound form, because we get a transfer of electrons because of those periodic trends and the big differences. That's also why when we put two non-metals together, they both have the same type of periodic trends. They both want to hang on to their electrons. So the best that they could do when they go to bond is we'll just share. We're not, nobody's going to get rid of their electrons. We'll just share the electrons. Any questions on any of that? All right, we're laid up there.